looked at proof by induction the last time. Questions on any of those? All the questions will come right before the homework's due. It's like, I haven't had it.
Yeah, pretty much.
Okay. Okay, well, today, we've been looking a little at how we discover proofs and the realization that we don't just see, oh, I know it's this. We don't just know all 5 or 6 steps to write down. We get in and we explore and sort of have a moment and then figure out how we're going to write that down. So we're presented as well, we know this is true, and then this is true, and well, then this is true, and therefore this is true, and thus we reach our conclusion. So that's how it's presented. Now, if we see a proof, it's typically presented that way. And normally, if we see the proof, we kind of read through and think, yeah, makes sense. But what we want to look at today is like number 3 over here on the standards for mathematical practice. Critique the reasoning of others. We're going to look at some what are called fallacious proofs. See if we can find the error in the proof. That somebody's put together a proof that it really isn't a proof, and so we're going to see if we can figure out, well, what's wrong with that proof. So we'll start with this one. Let me see if I can make it bigger. So the proof that 1 equals 2.
Huh?
Yeah, so I mean, that's where it is, huh? So we're sort of clued off in the beginning, wait a minute, there's probably something wrong in this proof. But our challenge is to look and see if we can figure out, okay, what is wrong in this proof? Because we're pretty convinced something is. We know 1 is not equal to 2. So something's wrong in this proof somewhere. And our challenge is to kind of look at what's presented and if we can figure out, well, where's the mistake? And this one is actually set up. We can click on a sept number and it will tell us if that's where the mistake is or not. Doesn't give us many reasons. So let's just kind of start. I mean, we're going to let A equals B. Okay. What'd they do here?
Multiply both sides by A.
Yes. And can we do that?
Yes.
All right, we can do that. Then what?
Added
Added A squared to both sides. And we can do that too, right? Combine the like terms. What'd they do then? Subtracted 2AB from both sides, and we can do that too, right? As long as we do the same thing to both sides, equality is preserved. Combine like terms. Factored out. And then,
Divide by
yeah, A squared minus AB, and we get 2 equals 1.
Wouldn't A squared minus A times B, since A and B are equal, wouldn't that be 0?
So we can cancel this from both sides provided it isn't 0. And in this case, A squared minus AB not only could be 0, but by the way we started it, actually is 0. So we do have to watch when we cancel things on both sides to make sure we're not canceling a 0, because anything times 0 equals anything else times 0. And we could have made 1 equal to anything with this argument of canceling a 0 from both sides with that. So you think it's step 8 here, the canceling from both sides. Congratulations, you correctly identified. Division only makes sense when we're dividing by non-zero. Here A squared minus AB equals 0. And so we can't divide both sides by that. And then they say a little bit more related to that. there was a fallacious proof of 1 equals 2. Let's try this one with complex numbers. You remember complex numbers? I, the square root of negative 1. So we're starting with negative 1 equals two forms of negative 1, right? If we take the square root of both sides, complex numbers, square root of the quotients, the quotient of square roots. Square root of negative 1 in each case is I. Divided both sides by 2. So divided both sides by 2, then what do we do? Yeah, added the same thing to both sides. Multiplied by I. So we get I squared when we distribute through, and some more when we distribute through, and so minus a half plus 3/2 equals 1/2 plus 3/2, 1 equals 2. And again, our thought should be, well, something's got to be wrong, because I know 1 doesn't equal 2. But can we figure out what is wrong?
Is that I squared, is that negative 1?
Yes. So you would say, like, what, step 9, where we took...
I was just asking if I squared did transfer to negative 1.
Yeah. So, yeah, I squared is negative 1 from the definition of complex number, and I over I is 1 from that. Well, as I said, this one is much more subtle. I mean, if we look at that a little bit more, I mean, they did some other funky stuff. What would seem to be a more natural thing to do maybe at that point? Cross multiply maybe? Which is going to give us what, I squared equals 1? Wait a minute, I squared is supposed to be negative 1. So somewhere there's a mistake before here in terms of how we've approached this. So there's kind of a sense here we can see the mistake. I mean, down here we realize that there's a mistake because 1 can't be 2, but even here there's a mistake. I think the answer is kind of in step 3. This innocent-looking step is in fact quite wrong. The problem is there's no rule that guarantees the square root of A divided by B is the square root of A divided by B, except when they're both positive. And if this surprises you, think about the question, why should it equal that? And the reason has to do with what the square root is. Well, square root of negative 1, once we kind of move into the complex numbers, square root of negative 1 we think of as I. We can also think of it as minus I. So there's kind of two values who would give us that number squared being negative 1. I is not the only right answer. I mean, the square root of 4, we kind of have to think sometimes, depending on where the square root shows up, is our answer just 2, or are we looking for plus or minus 2? If we were trying to solve x squared equals 4, we could solve it in terms of the square root, but hopefully we realize, wait a minute, it's plus or minus. X could be plus or minus the square root of 4. Whereas if we just see the square root of 4, we kind of understand we need the positive square root. Well, with complex numbers, turns out there's no really positive square root. Complex numbers, we really can't talk about positives and negatives. I mean, we couldn't, I mean, if we look at I is either going to be greater than 0, equal to 0, or less than 0. That's the trichotomy. If you look at any number and you have order, one of those three has got to be correct. You compare two numbers. If you are able to compare two numbers, one of them's bigger, or the other one's bigger, or they're exactly the same. Okay, would everyone agree they are not the same? So the question is, okay, well, what can you do with I? If I is greater than 0, we can multiply both sides by I. And our property of numbers is if we multiply both sides by a positive, the direction of the inequality stays the same. But what's I squared? And -1, and I times 0 is 0. Well, -1 is not bigger than 0, so that can't be right. So it has to be one of these three, and it can't be the first or the second. Well, it must be the third, but let's sort of look at the third as well. Suppose I multiply both sides by I. But over here, if I is less than 0 and I multiply both sides by I reverse the direction of the inequality. If I really can be signed positive or negative, if there really is a way I can order it, and I'm assuming it's negative, I've got to reverse the direction of the inequality, and again I get -1 is greater than 0, and that can't be. So there are things that the technical term is that there's no ordering to them. And the complex numbers, there's no real way to put them in order. Integers there are. Rationals there are. Reals there are. We can talk about which one's bigger than which one. But you get in the complex numbers, there's no good way to put and say, how does I relate to 0, and for that matter, then anything else. There's no order that we can put on it. Okay, let's go back and look at another one. Here's one, has to do with mathematical induction. So we're just doing mathematical induction. This proof will attempt to show that all people in Canada are the same age by showing by induction that the following statement is true for all natural numbers n. So the statement is, in any group of n people, everyone in that group has the same age. But we shouldn't be shaky on mathematical induction, so we'll just kind of dive into the proof. So, step 1, as we typically do mathematical induction, we start with the base case if n equals 1. So in any group that consists of just one person, everyone in that group has the same age, because after all, there's just one person. Therefore, the statement's true when n equals 1. And as is kind of typical the case for mathematical induction, S1 is not so much proving, it's verifying that really does work. The next stage is to prove that whenever S sub n is true for one number, say n equals k, it's also true for the next number. And so we do this by assuming, one, that in every group of k people, everyone has the same age, and then deducing that in every group of k plus 1 people, everyone has the same age. So we're going to look at a group of k plus 1 people. And we want to show they've all got the same age. So to do that, we just need to show that if P and Q are members of G, then they have the same age. So we consider everybody in G except P. So we pull out one person. Well, now we've got a group of k people, and they have to all be the same age. That was our assumption. Similarly, Similarly, if we consider everybody but Q, again, that's a group of K people. by our hypothesis, for the induction hypothesis, they have to have the same age. Now let R be somebody else in G other than P or Q. Q and R. Q and R belong to this group, and so they're the same age. P and R belong to this group, and so they're the same age. Therefore, P, R, and Q are all the same age, and so P and Q have the same age. And so everybody in group G must be the same age. And then the proof is complete because we've done what we were supposed to. Proven it for n equals 1, and then if we assume it's true for n equals k, we can prove it's true for n equals k plus 1. So it's true for all n. So a fairly lengthy proof here. Yeah. Hopefully, as we think about it, maybe it's not quite as obvious as the 1 equals 2 that there's some problem with it, but hopefully we think about it. Everybody in Canada is not the same age. So something's got to be wrong here. Our challenge is to figure out, okay, where's the mistake? Because somebody's written, and intentionally written what they intended to be a fairly convincing argument, with a mistake in there somewhere to try to lead us astray. And our challenge is to try to figure out, okay, where have they tried to lead us astray? Well, what have they done that was not allowable here?
So it has to be, what, k plus 1 and k, right?
Mm-hmm.
So they prove that since n is k or whatever, then they proved it for n equals 1.
Mm-hmm.
And then it sounds like from the proof they proved it for n equals 3, but you can't, because they have 3 different people specified. But then what about if there's just 2 people?
Okay. And therein, is the fallacy that this step 3, let R be someone else in G other than P or Q. If K is only 2, we can't do that. If K were 3, or actually I guess if K plus 1 were 3, then K is 2. So really it's the K equals 1 case that's problem moving from 1 to 2. Let R be someone else. That is the problem. There's no guarantee there's somebody else other than P or Q. As we move from 1 to 2, if there are 2 people in there, you pull one out. Well, yeah, they're all the same age as everybody else. You pull the other one out, well, yeah, they're all the same age as everybody else in that group. But there's nobody in common that you could say, oh, well, they're all the same age. Because in a sense, you were assuming to prove they're all the same age, we were talking about 3. K plus 1 being 3, so K was at least 2. And so the proof would work if we could make the step from 1 to 2. So if we could somehow conclude that in every group of 2 people, they were always the same age, then we could go to 3 people, and to 4, and to 5. It's just that step from 1 to 2 that's a problem. And that's where the problem lies. But it was a very subtle error to try to figure out, okay, where exactly is there a fallacy in this? So, just because you see a proof doesn't mean it's automatically true. And depending on how long the proof is, it can take a lot of work to make sure every step really is true. Because it's kind of easy to read and say, oh yeah, that makes sense. Oh, that makes sense. Yeah, that makes sense. I remember my thesis advisor, when my thesis was going to get defended, I had a committee, I think there were 4 or 5, and somebody on the committee had asked, didn't really want to go through and verify all the things I had proven. You know, I'd asked my advisor, is this, you know, is everything really true? And he's like, well, yes, we had checked it as we went along. So one other person had checked it, but certainly there's nothing that would indicate, you know, that on a really complicated proof, a couple people might find error, make errors. And I think when Wiles first came out with his proof of Fermat's last theorem, his first proof, somebody found a mistake in it. And so they had to look, okay, you know, is all my work useless because of this one mistake, or can I do something to kind of fix this one mistake with that? So most of the time, in math, nobody intentionally makes a mistake in presenting a proof, because in math we don't want to fool people. Other places, though, that can certainly happen. People can be making an argument and intentionally put in something that's a little misleading to try to think, well, if I can just draw you down a certain path, then you're going to reach the conclusion, you know, I want you to reach. In a certain sense, a lot of advertising is sort of that way. You know, here's this product. You really need this product, you know, to make you, I don't know, strong, handsome, beautiful. I mean, most advertisements kind of do that. And oh, you know, our product will help you achieve that goal. So that they're definitely setting it up in such a way that they want. They sort of make you feel there's a lack, and they can meet that lack, fill that need in your life that maybe you didn't even know anything about until you saw that particular commercial. And with a lot of commercials, hopefully after you watch it, you realize, that's silly, I don't have that need in my life, but you know, it can happen. Let's see. So, okay, go to one other.
Welcome. Here's the question. Does 0.999 forever equal 1 or does it not? This is the age-old question that drives students and teachers simply nuts. It's a very interesting question and it's a valid one. It's absolutely every right to be confused by it. Let's talk about 0.99. Here it goes. 0.999 dot 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 forever. Is it 1 or is it not? Well, most students would argue this way. 0.9, that's certainly not 1. That is smaller than 1. What about 0.99? That too is smaller than 1. We're closer, but it's smaller. What about 3 nines? 0.999. I'm afraid that's still less than 1. Even if I were to draw 50 nines, that would still be smaller than 1. In fact, no matter how many nines I draw, the answer is always smaller than 1. Therefore, a whole bunch of 0.99s going forever would still have to be smaller than 1. It will never actually get to 1. Now that's a very decent line of thought, and many people will argue that way forever and a day. I have a question about that. So let's just remove this moment. People, for some reason, don't seem to object to 0.3333 forever being 1/3. My reasoning here is the same argument actually applies the same problem. Look at this. If I was just write 0.3, that would not be a third, that would be less than a third. Well, 0.33 is certainly smaller than a third. 0.333 is smaller than a third. If I draw 53s after the decimal point, that is still a number smaller than a third. By the same reasoning, I have to say that this guy is smaller than a third. What's curious? Folks, for some reason, do not object to saying 0.333 is a third, but they will object to saying 0.999 is 1. Well, what's the difference? Why do people like this one and not like this one? Well, I have a feeling it's to do with long division. Let's go back a step. Let's actually go back to 1/3 for long division. Let's divide 1 by 3. Here goes. Set a long division symbol. We write 1, probably a whole bunch of decimals. Here goes 1.000, and dot 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 forever. It's very curious. We wish to divide this by 3. Well, here goes. How does long division work? How many times does 3 go to 1? Not at all. So don't try it. Bring that 1 over and make this 10. Ask how many times does 3 go to 10? Well, certainly goes to that 3 times, leaving 1 over. Carry the 1. Left with how many times does 3 go to 10? 3 times, 1 over, carry the 1, and so on. So actually, if you perform a long division, you're fairly stuck in an infinite loop. So it seems reasonable to believe that we have staring before our face a true statement that 0.333 forever is a third. Well, I can actually argue exactly the same way to say that 0.999 forever is 1. It's strange when we do this following. Let's divide 1 by 1 using long division algorithm, but I'm not going to be very efficient. Here's the number 1 with a whole bunch of zeros. And I'll divide by 1. Now, of course, I'd say every times 1 goes to 1 and we're done with it. But I'll be a little bit sneaky. Let's say 1 doesn't go into that at all, and still has a remainder of 1. It's very true. I'll carry the 1 and make 10. And ask myself, how many times does 1 go into 10? Well, so it goes in 10 times, but it also goes in 9 times with a remainder of 1. Let's carry the 1. Ask me how many times 1 go into 10. I mean, be inefficient. It goes in 9 times with a remainder of 1. Remainder of 1, carry it. How many times does 9 go into 10? But 1 goes to 10, 9 times, and so on. So in some sense, long division even wants to suggest that 0.999 forever is 1. I admit it's very strange, inefficient long division, but there we are. Well, maybe long division is the way to go. I don't know how to argue it really. So let's try a different tact. Most people do the following. If you're looking at an infinite decimal, like here goes 1, 2, 3, 4. Let's pretend we don't know what it is. And one trick is to give it a name. Let's call it Frederica. And perform algebra on the statement. Let's multiply both sides by 10. Well, 0.333 times 10 would be 3. 0.333 forever would give me 10 Frederica's. Well, 3.333 forever, would be 3 plus 0.333. That's another way of writing on the left-hand side. Let's do 10 Frederica's. Well, 3 plus, what's this guy? Plus Frederica again is 10 Frederica's. So let's subtract Frederica on both sides. 3 equals 9 Frederica's. Gives me Frederica is 3 ninths or 1/3. There it is. Let's do the same argument. Let's look at 0.999 forever. And perform the same sort of algebra on it. 0.999 forever. Let's do the fun part. Give it a name. Let's call it George. Alright, here's George. Apply the same algebra. Let's multiply both sides by 10. 9.99 forever. Would be 10 George. Well, what is 9.99? Well, it's really 9 plus my original guy. That's still 10 Georges. So I've got 9 plus George is 10 Georges. Now, subtract George on both sides. 9 must be 9 Georges. And look at that. That is telling me George must be 1. It seems that I've got an ironclad argument now that 0.9999, here it is, 0.9999 has to be 1. Well, I have to say something. That is actually not very satisfying. Let me blow this argument out of the water. Let's try it again. We did an infinite number of 9s to the right. What if I asked about a number that was an infinite number of 9s to the left? And asked what value is that? This is very strange. But let's apply exactly the same mathematics. Let's start by giving a name. Harriet. Let's multiply by 10. Multiply a number by 10 just adds a 0 to the end. So the whole infinite number of 9s, the 0 at the end, would be 10 Harriets. Well, this guy, whoops, we're on Harriet. 10 Harriets. Look at this guy. It's the original Harriet minus 9. This is really a whole bunch of 9s. Ending in a 9 minus a 9 is 10 Harriets. That is, the original Harriet minus 9 is 10 Harriets. Subtract Harriet on both sides. Negative 9 is 9 Harriets, which tells me Harriet is negative 1. It looks like I've just proven the number, infinite number of 9s to the left is negative 1. What do you think of that? Now, this is very curious. When I give this argument to folk, they usually balk at the idea of a whole bunch of 9s to the left being a nice negative number. And the reason they argue about this is the following. This guy is really 9, that's that guy, plus 90, that's that 9 there, plus 900. And it looks like the mathematics has just proven this equals negative 1. 9 plus 90 plus 900 plus 9,000 plus 90,000 and so on, as negative 1. Nonsense. So what's going on? Well, this is where there's a human element to mathematics. the math we did shows the answer must be 1. The answer must be 1. If we choose to believe the whole bunch of 9s going from the left as an answer, then the answer must be -1. That's all the mathematics has done. It's never addressed this question. Most people like to believe this guy does have an answer, in which case the answer is 1. Math says that. Most people choose to believe this guy doesn't have an answer, in which case it doesn't matter what the math says, you don't believe it has an answer. This is very interesting. So, does 0.999 equal 1 or does it not? Well, the question is, do you believe it has an answer? If you think yes, then the answer is 1. Yes, it does equal 1. If you think no, and you have every right to believe no, then there is no answer to the question. So, well done, students. You're absolutely right to question it and balk at the idea. But if you ever take a calculus class, you might have reason to believe it has an answer.
So as we see arguments, we need to kind of take them with a grain of salt and realize there's some things, there may be some subtle things there that we didn't realize. Here's 9999 to the left equaling -1s. Another one we sort of look at and think, that can't be. But why can't it be? If we believe the 9s, everything doesn't have an answer, okay, but if it does, then the answer would be -1. Another video that we kind of have to think carefully about what's going on. Let me see if I can find this one, or one of these. One of these will work. I don't remember which one's better.
Just up to you, 13 apiece. You want what? 13 apiece. 13 apiece? Yeah, 7 ounces. Yeah. Each has 13. You only got 28. That's right. I had 28 dollars and 713. I get it. 713 to 28. Yeah. That's ridiculous. 7 times 4 is 28. Not 7 times 13. 7 times 4 is 28. Sure. 7 times 4 is 28. What's one of those cheap school? I mean, 7 times 13 is 28. That's ridiculous. Yeah. What's the matter with you? I couldn't smoke it out. Okay. You had it. I figured it out myself. Prove that to me. I'm not going to get it. That's ridiculous. Go ahead. Oh, come. There's no sense to your argument. Just so. Go ahead. Now, there were 7 ounces. That's right. That's a 7. Now I'm going to the black and prove it to you. Now, $28. $28. Now, you claim the 7 goes into 28 13 times? Prove it to me. Now, 7 to 2. What do you mean 7 to 2? 7 the black with the 2. No matter how much you try. We know that. You couldn't even push that big 7 to that little bit. Certainly not. Therefore, we can't use it 2. What are you doing? Well, let Dizzy hold it. Dizzy, hold that 2 for me, please. Thank you. I'll use it later. What is this all about? Now, 7 to 8. 1. Now, we're going to carry the 7. Carry the 7. We're going to carry the 7. Carry. Still a little heavy, so I'll put it right down there. 7 to 8. 1. Now, a minute ago, we didn't use it 2. What do you mean? We're going to use it now. Use it? You make it 2. Thanks. Okay. Put it right
just because he had an argument didn't mean it was a valid argument in terms of that. And you know, he actually had 3 arguments, right? 7 and 13 should give you 28. So let's see, I've got 3, I think, looking to be math teachers. So what do you think? You're going to have to read students' arguments and figure out where the fallacy is, where the mistake was. So how would you go about explaining where the mistake was in any one of those 3? Because we're thinking, oh, 7 times 13 isn't 28. 7 times 4 is 28. Where's the 7 times 13? So we have what? 7 into 28 once and then 3 times. Well, what should happen in that 1 and 3? Because in a sense it does go in once, then it goes in 3 times.
3 added together.
Yeah. Because we didn't, it was once and then another 3 times. It was not 10 times and then 3 times. It was just once and then 3 times later. So we should add them, which does give us the answer we're more familiar with. 7 should go into 28 4 times, not 13. What about the multiplication? 13 times 7.
That's really multiplying it by 10 there, not just 1.
Yeah, so the 7 times is really 7 times 10. The 7 should be over here. So we should get 91 there, but if you're not careful in moving things over, you get the place values lined up incorrectly, and you get an answer that's not correct. Then there was what, the 13 sevens, or 7 13s. And added up 21, which is correct. But then the other 7 again is not just 7, it should be 70, right? Because we're adding up 7 10s, not just 7 1s. But it certainly does kind of point out that a slight error in our thinking can produce an argument that looks reasonable, sounds reasonable, until you sort of identify where that fallacy is. You know, it can be hard to convince somebody of their mistake. So we're throughout the course going to be doing a sort of a reoccurring theme of that when we see a theorem, there are some assumptions, and that leads to the conclusion. Typically, the assumptions we give are just the ones we need to lead us to the conclusion. So if there's an assumption there, it's there for a reason, because if it wasn't there, the conclusion wouldn't be true. Something would be different about the conclusion. We would know it's true, different things. And that idea also comes into play, as you say, go on a mission trip. I mean, if you're on a mission trip and you assume you meet somebody on the street, they've heard about Jesus, something about Jesus, there's a place you could start. But if you go and assume they've heard nothing about Jesus, well, you would start in a totally different place. And you kind of have to know the culture well enough to know what is, you know, what kind of knowledge am I going to meet up with in general? And if there's no way really of knowing, well, you need to ask some questions to figure out what is the knowledge in general that they have before you decide, you know, how can I lead them to know about Christ if they don't know anything. It's certainly a different witnessing path than if they know other things. You've got to kind of figure out where are they coming from as you develop your witness, your testimony to them about who Christ is in your life. So there are lots of places where the assumptions that we have are affecting kind of what we do. Other places that I do assumptions, I'm going to guess a lot of you have cars on campus. You're running late to class, you got to your car, you get in. You're making an assumption. Your car is going to start so you can get to class. What happens if your car doesn't start?
You run fast.
You run fast, or you're late to class. I mean, you suddenly have to come up with something else, but I mean, whereas if you'd have known up front your car wasn't going to start, you'd have planned it better. Yeah, you'd have planned your time better, called phone a friend, or walked to class so you didn't have to run to class. Because you made a certain assumption, as long as it works, yeah. Or you got your car's gone, that would be bad too. That might even be worse than, your car doesn't start.
Yeah, I'd rather have a car.
Car doesn't start, well, that's a problem you can fix later.
Yeah, financially, he's a little bit less.
But, still very much some assumptions on that. I'm going to guess Braden. I'll pick on Braden again here. As a lineman, on certain plays, you might have an assumption on what the defender is going to do.
Based on alignment and a whole bunch of different areas.
Yeah, but you sort of look and you figure out what you think they're going to do, so you block accordingly. Do you ever assume incorrectly?
All the time.
All the time. Yeah, typically that's not good, right? If you assume one thing and that's not what happens, well, the play doesn't go as well as it would have otherwise. And so, you definitely want to try to take in all the variables. And I'm going to guess there are probably sometimes you're not totally sure what they're going to do. There are ways they can disguise what they're going to do. And so you're thinking, well, maybe they're going to blitz, maybe they're not. And you sort of have to think, well, what sort of worst case scenario, maybe I should prepare for that. And if it doesn't happen, what then?
Guys.
Huh?
I got 4 other guys.
Yeah. Well, and that's a team. And in terms of the team, you're making the assumption the other 4 guys are going to do their job. You need to do your job, and if at some point you realize somebody else didn't, hopefully you can help out. But the whole point of a team is the assumption that everybody's going to do their job, and if everybody doesn't, well, the result is somewhat different. But the assumptions that we go in definitely do affect how things work out. If you had a teammate that your assumption was they don't know what they're going to do, they don't know what they're doing, that's going to affect how you play the rest of the game, right? Because you're going to think, not only do I have to do what I'm supposed to do, I've got to help cover what he's supposed to do because he's not up to doing that, and you may not do your job as well because now you're trying to do too. And so the assumptions you go in definitely affect how you proceed in the game. So we will at some point be doing a paper on how assumptions in math and how changing the assumption can change the outcome, change the theorem, how that kind of relates for us in life. That if we have a certain assumption, we could go one way in life. If we have another assumption, that will make it a totally different set of choices. Paul in Athens saw the idol to the unknown God. It was a perfect place to start. You have this God you don't know about. Let me tell you who it is. So he could see kind of what their assumption. There's probably some God we missed, so we'll just have an idol there for that God that we missed. Well, Paul could build on that. Whereas if he was in a place that didn't have any kind of gods, well, he would have had to have built a different argument at that point. So. Monday we will proceed into section 1.4, but I thought this was a good time to kind of just look at some proofs and that whole idea of proof and realize that just because we see a proof written doesn't mean, that we can just read it and say, that makes sense, we're good. Because there are times maybe it's not all good. And so we need to think as we put proofs together? Have we really said everything? Have we done correct, correct reasoning as we move from one step to the next all the way through? So I will see you Monday.
Hey, y'all clean up that